Hello, welcome to Hawk Math. Today we're going to be doing the integral from 0 to 1 of x times the fractional part of 1 divided by x times the floor of 1 divided by x dx. Now my first thought when I look at this integral is it's very messy because we have the fractional part of 1 divided by x and the floor of 1 divided by x while also having an x in the integral. And I don't really like the idea of taking the floor or fractional part of 1 divided by x, so I think I want to get rid of this 1 divided by x. And the way I'm going to do this is I'm going to try u sub of u equals 1 divided by x. So that would make du equal to negative 1 divided by x squared dx, or negative 1 over u squared du equal to dx. Okay, so now plugging in, we have the integral. Well, at 0, u is going to be infinity, and then at 1, we will have 1, and then we have x, which now becomes 1 over u, and we have the fractional part of 1 divided by x, which is u, and then we have the floor of 1 divided by x, which is also u. And now we have dx, which is equal to negative 1 over u squared du. Okay, now I'm going to use this negative sign to change the bounds of integration, and I'm going to combine this u squared and u on the denominator to rewrite this integral as the integral from 1 to infinity of the fractional part of u times the floor of u divided by u cubed du. Now, this is in a little bit of a nicer form because we only have u's, and we don't have really any 1 over u's. But where do we go from here? Well, my initial thought is that we have both the fractional part of u and the floor of u, which kind of repeats every whole unit. What I mean by this is, for example, on the interval from 1 to 2, the floor of every single value on the interval is 1. And on the interval from 3 to 4, the floor of every value on there is 3. So maybe we can split this up unit by unit and take the sum of all of those integrals for each individual section. Now the way I want to approach this is by taking the summation from, let's start n equal 1 to infinity, then we're going to have the integral from n to n plus 1. Now, just making sure this does what we want it to, we have the integral from 1 to 2, and then we're going to have to add the integral from 2 to 3, then we're going to add the integral from 3 to 4, and then we keep going to infinity. That should give us the whole bound. Now, what goes on the inside of the integral? Well, we know the fractional part of u is equal to u minus the floor of u. And you can think about this for a little bit, but it should be pretty obvious about why this is. And now, on the interval from n to n plus 1, the floor, since we defined n to be these integers, the floor of u from that interval is just going to be n. So, from the interval from n to n plus 1, we know that this first part, the fractional part of u, is just going to be u minus n. And then we have the floor of u is just n. And then all over the denominator of u cubed du. Now, this integral is pretty easy to compute because all we need to do is simplify it out and it just becomes a polynomial. So this is equal to the summation from n equals 1 to infinity of the integral from n to n plus 1 of, well, we have a u times n over u cubed, or n over u squared, minus an n squared over u cubed du. Now integrating, well, this is going to be equal to the sum from n equals 1 to infinity. Well, when we integrate n over u squared, we're going to get negative n over u. Then we're going to have a plus n squared over 2u squared, and then evaluate that from n to n plus 1. Okay, so now plugging in our bounds, we have the sum from n equals 1 to infinity of, well, plugging in n plus 1 over here, we have negative n over n plus 1. Then we have a plus n squared over, well, we have 2 times n plus 1 squared. Okay, and now we need to subtract plugging in n. So we're going to have a plus n over n, because this is negative, and then we're going to have a minus n squared over 2n squared. And this is going to be summing from 1 to infinity. Well, we see this simplifies a decent amount, so we can rewrite this as a sum from n equals 1 to infinity of negative n over n plus 1 plus n squared over 2 times the quantity n plus 1 squared. And this will become 1, and this is minus 1/2, so we have plus 1/2. Okay. Now, in order to finish this, I don't really like the idea of having this n plus 1 on the denominator, and maybe we can try re-indexing it so that we have an n minus 1 on the numerator and an n on the denominator. So when we re-index this, we're going to have the sum from n equals 2 to infinity. You could write this as a different variable if you wanted to. We have negative n minus 1 over n, and then we're going to have a plus n minus 1 squared over, and then on the denominator, we're going to have a 2n squared plus 1/2. And this is a little bit nicer to deal with because we can expand out the numerators and combine like fractions. So doing that, we have the sum from n equals 2 to infinity of, well, right here, I'm going to write this out. I'm going to do this term first. So we have an n squared minus 2n plus 1 over 2n squared minus n minus 1 over n plus 1/2. And now I want to combine all these fractions together and see what we get. So we have the sum from n equals 2 to infinity of, well, we can multiply this by 2n squared. So we have an n squared minus 2n plus 1. And then multiplying this fraction by 2n squared over 2n squared, we get that we can add, subtract negative 2n squared, and then plus 2n. And then over here, we're going to multiply this fraction by n squared over n squared, so we're going to add n squared, and all that's over 2n squared. Okay, now we see we have some cancellations. This plus 2n will cancel with this minus 2n. The minus 2n squared will cancel with this n squared and this n squared. So now we're just left with the sum from n equals 2 to infinity of 1 divided by 2n squared. Now this should immediately jump out to you as very similar to the Basel problem. So we can bring out this 1/2 in front of the summation. So you have the 1/2 times the summation from n equals 2 to infinity of 1 divided by n squared. Now this is almost the Basel problem, except that we're starting from 2 and not 1. So this is famously known to be pi squared over 6, but then we have to subtract where it starts off at 1. So this is equal to 1/2 times, well, the sum from n equals 1 to infinity of this is pi squared over 6. Then we're subtracting when we plug in 1, so 1 divided by 1 squared is just that. And so now, simplifying this all out, we have pi squared over 12 minus 1/2. And we are done with this problem. Thank you for watching. I really hope you enjoyed this video. Please like and subscribe if you want to see more like it, and feel free to leave any comments or suggestions down below.